Guys, it's dark, it's massive, and it's tiny. These are three indisputable pieces of evidence that a supermassive black hole exists. Space can be scary. The dangers that lurk in this vast expanse can be terrifying. While this applies to the entire concept of space exploration, one part that's always fascinating and terrifying at the same time is black holes. These powerful monsters have been the subject of countless studies around the world. Scientists are trying to figure out what black holes really are and what lies inside them. But that's all about to change. Neil deGrasse Tyson has just revealed something huge. Our black hole is less massive than the one at the center of the Andromeda Galaxy, our nearest major galaxy. That's why we envy black holes. I think so that we're finally seeing what's inside black holes, and it might blow your mind. So join us on this intergalactic journey and answer one of history's most frequently asked questions. What is a black hole? Created by a massive explosion, a black hole's mass is concentrated in an extremely small area, creating a gravitational force so strong that nothing, not even light, can escape. Once something is inside, it's there forever. These energetic forces come in many sizes, from stellar black holes, which can be many times the mass of our Sun, to supermassive holes that exist at the centers of galaxies and can be millions or even billions of times the mass of our Sun. Scientists have been observing the effects of black holes indirectly for decades now. With each piece of data we uncover, hundreds of secrets are revealed. Although they seem so big and powerful that they can't possibly have an origin story, they do. Black holes don't just exist in space, they're created. They require the remains of massive stars that have exhausted their nuclear fuel to form. These stars undergo a supernova explosion, a spectacular event that marks the end of their lives. In a supernova, the outer layers of the star are ejected into space while the core collapses due to gravity. Not all collapses are the same. If the core mass is several times that of our Sun, gravity will overwhelm all other forces, causing the core to collapse inward. This contraction is so intense that it compresses the mass into an extremely small volume, creating an object with a gravitational field so strong that nothing can escape its grip, thus creating a black hole. The size of a black hole is determined by its mass. Stellar black holes, the best known type, range in mass from a few times to several tens of times that of our Sun. At the center of a black hole is a singularity, a region of infinite density and curvature of spacetime. According to our current understanding of physics, the laws of nature break down at this point, and our conventional theories cannot fully explain what is happening inside a singularity. To truly understand the nature of singularities, we need to think creatively. In the world of physics, a singularity refers to a point in spacetime where certain quantities become infinite or indefinite. These singularities appear in a variety of theoretical contexts, such as at the beginning of an expanding universe, often called the Big Bang singularity, and inside black holes. When we study the Big Bang singularity, a fundamental challenge arises. According to this theory, the universe began about 13.8 billion years ago in an extremely hot and dense state. But when we go back in time to this initial state, the equations of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics cannot fully describe the conditions that prevailed at the time of the Big Bang. To resolve this problem, a theory that combines general relativity with the principles of quantum mechanics is needed. Black holes contain singularities at their cores. These are regions where gravity becomes infinitely strong and spacetime becomes strongly curved. According to general relativity, matter and energy falling into a black hole will reach a singularity and become infinitely compressed. This concept goes far beyond our current understanding of physics, which adds to the problem. The challenge of singularities has led scientists to search for a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics. Quantum gravity seeks to provide a framework that explains the behavior of spacetime on both cosmic and subatomic scales. Such a theory has the potential to shed light on the nature of singularities and how the universe actually works. One approach to solving the singularity puzzle is the theory of loop quantum gravity. This theory holds that at extremely small scales, spacetime is quantized, meaning that it is made up of discrete, indivisible units. These basic units are often called spins or lattices. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This means that spacetime is not considered as a continuous and infinitely divisible entity but rather as a collection of discrete elements. These discrete units of spacetime are often considered as interconnected loops or networks that represent the fundamental structure of the universe. Within the framework of loop quantum gravity, singularities associated with black holes and the Big Bang can be resolved. One of the key ideas of this theory is that at extremely small scales, the discrete nature of spacetime prevents the emergence of infinite density in curvature leading to singularities. For example, in classical general relativity, in the context of black holes, loop quantum gravity suggests that as matter collapses towards the core, the structure of spacetime becomes increasingly compact. This size prevents matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters quantum rebound near the core, where it bounces back and begins to expand again. This scenario leads to the formation of a new region of spacetime inside the black hole, often called a quantum black hole or recovery region. Stellar black holes are the most commonly observed type of black hole in the universe. They form after gravitational collapse at the end of a massive star's life. Once a massive star has used up all its nuclear fuel, the outward pressure created by nuclear reactions can no longer counteract the gravitational pull within. Gravity becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a stellar black hole. As the star contracts, it becomes extremely compact, packing a significant amount of mass into a very small volume. As a result, stellar black holes typically have masses ranging from a few times to about 20 times the mass of the Sun. Despite their massive size, they are remarkably small. Their diameter is only a few kilometers, which makes them extremely dense. The enormous density of a stellar black hole leads to the formation of an event horizon, a limit beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the black hole's gravity becomes so strong that any object or information passing through it will be trapped in the black hole forever. This gives us intermediate mass black holes. Although the exact mass range for intermediate mass black holes is still something that scientists are still refining, it is generally thought that they range in mass from thousands to tens of thousands of times that of the Sun. These giant monsters occupy the central regions.